Hello, my name is Ang. This is
Bảo.
and together we represent our group called Vietnamese
Bảy Chợ.
Yeah, okay. And today we'll be presenting the subject of the number e, natural exponential, and natural logarithm. So I'll pass the mic to my colleague here, Bao, and we'll begin with our presentation.
So let's start off with the number e. It was introduced by Jacob Bernoulli in 1683 as a solution for the continuous compounding interest, which will be explained by Ang later. So as you can see right here, the number e is defined by the following limits. So let's consider these expressions: 1 plus 1 over n and all raised n. As n become larger and larger, these expressions grow ever closer to the number e. So let's have an example. So when n is equal to 10, these equations will be approximately equal to 2.5937. Let's have another example, like when n is equal to 1000, and these equations will be approximately equal to 2.7169. So let's move on to natural exponential functions with n.
Thank you, Bao. I'll take it from here. So meet the natural exponential function, which is y is equal to e to the raised to the power of x. Now, this graph here is this graph of this graph, and there's nothing. It's not really special currently to you guys, but further down along the line, this will be a very important function. Why is it? Well, I can give a demonstration here. As you can observe from the graph, the slope of the natural exponential function at any point is equal to its area, which in turn is equal to the function itself at that point. So for example, at x equal to 1, we will have e raised to the power of 1 will be e. So the slope of that point will be e, and the area of that point will be 2.718 blah 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 blah, which is, you guess it, e again. And both of these properties meant that this function is of tremendous importance to calculus itself, because the slope of a function is essentially what we do in when we take derivatives. That's all that we do. We take the slope of the function. Therefore, its property that the slope of itself at any point is itself, the value of itself at that point will be valuable to derivative. And for integral, it's all about computing the area of the graph. Therefore, the other property of a natural exponential function, that its area is equal to itself, area up to a point is equal to itself up to that point, is again vital to integral. But currently there's not much going on with natural exponential, so we'll stop here and we'll move on to my colleague Bao for his next part, which is natural logarithmic functions.
So the natural logarithm functions, denoted by natural logarithm of x, is an inverse exponential function with base e. So because it is inverse function of natural exponential, by reflecting it through x equal to y, we have the function for natural exponential. So now let's move on to the properties of it. First, it will change the base formula with any positive number with a. We have logarithm base a of x is equal to natural logarithm of x over natural logarithm of a. So here's the proof for it. Let y equal to logarithm base a of x. And then we have a to the power of y equal to x. So let's see here. Natural logarithm of a is equal to natural logarithm of x. And the final equations is logarithm base a of x is equal to natural logarithm of x over natural logarithm of a. Besides that, we also have some other properties such as product property, quotient properties, and power property.
I'll talk in closer detail about the real-world application for Euler number. One of it would be to compute continuous compounding interest. This is a subject which we'll all learn in closer detail further along the line because we're all here to study economic in some shape or form. Now, the formula for non-continuous compounding interest would be A is equal to P multiplied by 1 plus R over N, and 1 plus R over N is raised to the power of N multiplied by T. Come with me to the board here. I'll show you in greater detail how all this works. A is the total amount of money that you have after the investment matures. P is your initial money invest in the project. R is the interest rate or the money that you gain from the interest from the project, and N is the number of times that project will pay money to you, and T is the number of years that this will go on to be. Let's take a project that matures in 1 year that pays you interest 2 times and pay you our interest rate. That would be A. So A would be equal to P multiplied by 1 plus R over 2 multiplied by 1 plus R over 2 again because there are 2 increments of payment. And so which will be equal to P multiplied by 1 plus R equal to 2 to the power raised to the power of 2. And this right here would be the total money that you have after the first payment is being paid to you. Multiply this again, multiply all this by 1 plus R over 2 again, you'll have your final amount of money gained from this project. As you can see here, P, therefore the final form of this formula is P multiplied by 1 plus R over N to raise to the power of N, and that's our non-continuous compounding interest formula. I didn't go into great details about this because we'll all study this at some point in our career, and I'm not sure I'm fully able to explain this in depth too. We'll move along this to our crowning jewel, the role that E will play in the Euler number will play in all this, which would be compounding interest. Well, continuous compounding interest, a special case of non-continuous compounding interest, if you will. So, when the amount of interest being paid to you is continuous, that means it will be like you will be paid, say, every single second of your life, every single second that projects will go on. So, that would means the limit of this A will be equal to the limit of N as N approaches infinity of P multiplied by 1 plus R over N to raise to the power of N multiplied by T, which would be our non-continuous compounding interest back then. I just explained to you. Now, because we're dealing with a real-world problem here, R is most definitely, I assure you, always gonna be larger than 0. Therefore, the limit of N as N approaches infinity will be equal to the limit of n over r as over r approaches infinity. And the equation will turn to this form. Now, as you can see, this is kind of familiar, isn't it? Well, that's because this is the definition of Euler number as Mr. Bernoulli have proved so long ago. So, the limit of n as n approaches infinity multiplied by 1 plus 1 over n is equal to the Euler number. Therefore, all of this equal to p multiplied by e raised to the power of rt. T is for outside because p here is a constant. So as limit law applied here, we can please remove from our side, and therefore we have our final ultimate formula for continuous compounding interest. Let's take a break from all that jazz about theories and numbers and Euler and multiply and fraction, and get away with all that. Meet Tony. Tony, as you can observe here, with his huge shotgun, his humongous bald eagle, and his "Make America Great Again" hat, is a gun-tooting, God-fearing, absolute alpha Chad of a specimen of a American. Now, Tony, like every God-fearing compatriot American is a absolute capitalist, and he absolutely hates the taxman for taking his money away. So, using force, as you can see here with his shotgun, he forced the taxman, the government agent here, weak, small government agent, to pay him his money back. Now, because he's so strong and he, or maybe due to the bomb that he planted in multiple government buildings, who could say? Well, the government has agreed to pay him his $1 with 100% interest rate. So after a year, that $1 with 100% interest rate would turn into $2 into Tony's account. Well, because he's as the absolute peak male specimen that he is, Tony figured it out early on that, well, what if we figure out the effect of compound interest, and therefore a possible way to glitch himself out of the matrix into infinite money? Well, as the increment of payment that he asked the government to pay him increase, he will receive more money. As you can see, from 1 raised to 2, now he'll gain $1.25 due to with 50% interest rate, 2 times, which would be $2.25 in total from his bank account, and for 3 times with 25% interest rate, because the government doesn't really have infinite interest money to pay him, with equal to 1.44 dollar paid to him, and $4 and so on. Now, as the increment of payment approaches infinity, for some reason, he doesn't receive more money. Why is this? How is this possible? Well, that's because he has discovered E. And in fact, you cannot get infinite money out of the government, which sucks for him, sucks for you and me too. But, well, such is life. So he shrugged this off and he went on his way. But at least he learned about the Euler number. So, as X approaches this amount of money, the net gain from interest he would receive would be E minus 1. And the interest rate here would be around, doesn't really matter. And in Tony bank account now would be the Euler dollar amount of dollars. I hope that clears things up for you regarding of compound interest with this with this very visual example. Thank you, Tony, and let's move along to the exercise part with Bao.
Let's move on to the most exciting part of this presentation, is the exercises.
Hooray!
So we got the first exercise right here. Minus 3 multiply e to the power of 5x equal to minus 99. So you can pause the video right here if you want to solve it by yourself, and then you can check for the answer later. Okay, so to solve an exponential equations, we must first isolate the exponential part, and then we can solve for the exponent by converting the equation to logarithmic form using these following equivalents. So basically there are 3 steps. The first one is isolating exponents. The second one is converted to the log form, and the last one is solve for x. So right here you can see we have already give you this solution in detail, and the solutions to this exercise is x equal to approximately equal to 0.699. So let's move on to the second exercise. It is also from similar to the first one. We also have 3 steps. Like the first is isolating the exponent, second is convert to log form, and last is solve for x. Okay, you can pause the video right here to solve it by yourself. Okay, so the solutions, the answers to this exercise is this one. Are you correct? Okay, so now move on to the final one. So you already familiar with the way we solve this kind of exercise. So we want to trick it a little bit. So we won't give you the steps, and you have to solve it by yourself. You can pause the video right now. Okay, so the solutions to this one is x approximately equal to minus 0.109. Are you correct? Congratulations.
Thank you for listening to our presentation. We're glad to have you here with us. And a personal thank you to the supporting cast and to my colleague here, Mr. Bao.